Class. This will be the video for section 9.3, mass conversions, but it also includes temperature conversions, and we will also, like all the word problems from chapter 9 are basically at the end of 9.3. So the mass conversion part of this is once we talk about the actual conversions, the process works the exact same as 9.1 and 9.2 conversions. So I feel like I don't need to go as depth with those. For the temperature conversions, rather than the conversion process we've been using, there are a couple of formulas. So that we'll be using those. And then for the word problems, well, then we'll just go through the word problems. It's word problems you're going to have to learn how to interpret. So we'll practice those. So for the lecture handout, I'm on page 3 of the chapter 9 notes. So let's just jump into these and have some fun. All right. So with like I said, I'm pretty sure this is the bottom of page 3. So some conversions. 1 pound is 16 ounces. 1 ton is 2,000 pounds. Now that's in the English system. In the metric system, 1 ton is 1,000 kilograms, but the English is 2,000. And officially, it's called a short ton. I don't know why for sure, but the metric ton is 1,000 kilograms. The English ton is 2,000 pounds. Now, for the metric system, the prefixes work the same. So 1 kilogram, so kilo is 1,000, and it's the bigger one. So 1 kilogram is 1,000 grams. 1 gram, when we talk about CG, so we've talked about this with centimeters. Didn't do a lot of milliliters, but centi means 1/100th. So there are 100 centigrams in a gram. And then when you see mg, which tends to get used more often, particularly like with medicine, it's a milligram. A milligram, milli is 1/1000th. So there are 1,000 milligrams in a gram. And I covered this in the metric video, but in case you didn't see that, one of the really nice things for me from a math standpoint about the metric system is that the different types of units are linked together. So this is one of my playing dice. I don't have this a little bit, like if you have a Yahtzee game or something that you'll see that dice are bigger than this. This is a little bit smaller, maybe about 2/3 the size of one of those regular size dice. So this is approximately a centimeter on each side. So when you look at the volume, that would be a cubic centimeter. And so a cubic centimeter is 1 milliliter, which that was also briefly mentioned in the 9.2 video, but that's what a milliliter is. And if you think about taking like 10 of these, so and make it cute, do 10 this way, do 10 up. That would be 10 times 10 times 10. That would be 1,000 cubic centimeters or 1,000 milliliters. Well, 1,000 milliliters would be 1 liter. So if you think of this in 3 dimensions, this would be a liter. And the cool thing about this with mass is if you fill up one of these little things with pure water, that would be a gram. So if you fill up 1,000 of these, and have that box about that size, that would be 1 liter. That's how much a kilogram weighs. So about that much water is 1 kilogram, which is approximately 2.2 pounds. So in the metric system, length, width, and length, volume, mass, they're all connected in one way or other. And water is what that connection of water is how we get from length and volume to mass. And then let's see on the next page, there's a couple more here. So 1 ounce is 28.3 grams. So we're going from English to metric, and 2.2 pounds is 1 kilogram. And so those are some of the metric. And again, there's we don't need these for, well, we might need these in the word problems, but these are like more of the English to metric conversions. A lot of these are going to be given directly in the problem. So one way or the other, these are, the English to metric ones you need to know, or sorry, you don't need to know, they'll be given to you in the problem somewhere. Okay, so let's just do some basic conversions, and then we'll get on to some more on a variety of problems. So 3 pounds to ounces. So as always, we're starting with our starting unit over 1. And what do we know about pounds and ounces? Well, 1 pound is 16 ounces. So the 1 pound needs to go on the bottom, 16 ounces on top. Pounds cancel. So now we're just doing a multiply problem. 3 times 16 is 48. So 3 pounds is 48 ounces. Again, with all these conversions, if you know a direct conversion from one to the other, and it's a one-step conversion, let's just do multiply or divide, and these fractions help you get that without guesswork. Right. How about number 37? 4.3, 4 3/5 tons to pounds. So how would you do that? Well, what do we do with a fraction? We don't like fraction. Like we use fractions to set up our dimensional analysis to know how to deal with the units, but honestly, we don't like fractions in our numbers. So how do you convert 4 3/5 to a decimal? Well, you can either convert it to an improper fraction, 4 times 5 is 20, plus 3 is 23/5, and convert that, or the whole number is going to be 4, so you can just convert the fraction part. So 3/5 is 0.6. So 4 3/5 tons is actually 4.6 tons. So if you have any fractional numbers, my recommendation is convert those to decimals. The one problem with decimals sometimes is they could go on forever, and then like if you don't round in the middle of the problem, you wait till round at the end because sometimes it may throw off your decimals just a little bit. Which is another reason you don't see a lot of fractional numbers in these conversion problems, just to avoid the rounding issue. Right, so we're starting with 4.6 tons. So we need to convert to pounds. What do we know about pounds to tons? Well, 1 ton is 2,000 pounds. So the 1 ton has to go on bottom. 2,000 pounds will go on top. And the tons cancel. So again, this is a one-step conversion. In this case, it's a multiply problem. So 4.6 times 2,000 is 9,200 pounds. All right. Pretty straightforward there. Let's do number 38. That way we a little bit more involved problem. So 0.3 tons to ounces. So now we don't have a direct conversion from tons to ounces. So how do we do that? Well, what do they have in common? Well, we know we can convert tons to pounds, and we can convert ounces to pounds. So we know that 1 ton is 2,000 pounds. And we know 1 pound, if you don't remember, where was it? It was 16 ounces. That's one of those things that's an English to English conversion. So those are not always going to be given. And I don't have those on my formula sheet. Yeah, if you remember, I have that formula sheet. On this formula sheet, this is pretty much English to metric, or in the area stuff that we don't use as much, I give you those. If there's something like 1 pound is 16 ounces, is something that you think you might forget, remember you are allowed a 1 page of your own notes in addition to this for the test. All right, so we started with tons, went to pounds, and then go from pounds to ounces. So this is a 2-step problem. Now, since we're going from a big unit to a very small unit, we're still going to be multiplying. And so it's just a coincidence that we end up multiplying most of the time, it feels like. If I started with ounces going to tons, then we'd be setting us all basically upside down. We do a lot of dividing instead of multiplying. But that's where, again, the fractions take the guesswork out of that part. So we know 1 ton, so it goes on bottom, is 2,000 pounds. Now we know 1 pound is 16 ounces. So everything on the bottom is 1, so we're just doing 0.3 times 2,000 times 16. 1 ton, 0.3 tons is 9,600 ounces. We did definitely did more like 2 and 3 step conversions in 9.1 than we did in 9.2, or which we'll do in 9.3. It's just if you don't have a direct conversion, that's when you're going to need more than one conversion fraction. Yeah. Let's do some metric problem. How about 164 milligrams to infinite? Okay, so we're starting with 164 milligrams, done over 1. So do we have a direct conversion from milligrams to grams? Yes, because milli means 1/1000th. And so there are 1,000 milligrams in a gram. Now we need that 1,000 milligrams on the bottom to cancel out the milligrams. So 1,000 milligrams is 1 gram. Now this is a divide problem, not a multiply problem. 164 divided by 1,000 is 0.164. Again, when you're doing metric to metric, you're always multiplying or dividing by a power of 10. So you're always just moving the decimal. You're not actually changing the original number. It's just, which direction does the decimal go and how far. All right. What about number 43? 43 is 200 milligrams to CG. Now we don't use CG near as much, but remember C by itself is centi. So that is 1/100th of a gram, whereas milli is 1/1000th. So do we know a direct conversion from milligrams to grams? Well, we know CG to grams, we know milligrams to grams. So again, this is going to be a 2-step process. So we're starting with milligrams. We're going to go from milligrams to grams, and then from grams to centigrams. 1,000 milligrams, gram, and then 1 gram is 100. Excuse me, 100 centigrams. So set this up, 200 milligrams over 1. And so now we need 1,000 milligrams is 1 gram. Milligrams is on top here, so it needs to go on the bottom here. So 1,000 milligrams under 1 gram. And now from grams to centigrams, 1 gram on bottom, and then centigrams on top. Now, this is again where I recommend multiply everything on top, multiply everything on bottom, do the division last. So 200 times 100 is 20,000 divided by 1,000. That would be 20 centigrams. So 200 milligrams is 20 centigrams. So even though, again, you may not be as familiar with the units like you might be with pounds or inches or something like that, as long as you know your conversions, trust your fractions to cancel out properly. And it's to me, this is a straightforward process once you, like I said, kind of have to trust your fractions and know how to set them up correctly. Fractions can be your friend. Sometimes people believe me on this. Not very often. All right, let's see. I'm looking for some English to metric examples. So on the next page, we have, let's see, let's do 54 kilograms. This is number 46 on the next page, to pounds. Now, this is definitely where you don't want to Google your conversion fractions or factors because, MATLAB, unless there's a random problem where somebody coded it different, they're going to use 2.2 pounds is 1 kilogram. I've also seen that 0.45 kilograms is 1 pound. do not use that one unless that's explicitly what the problem in MATLAB gives you. And the reason being, and where you get that is basically like flip of each other. So, if you do 1 divided by 0.45, you get 2.222 forever. So these are both rounded values, but the fact that they're both rounded means if you use this one when MATLAB is expecting you to use this one, your decimals at the end are going to be off, and that might be enough for MATLAB to count it wrong. Now, if this is a testing situation, I can handle the rounding issues on that. But in the homework and the quizzes, MATLAB is going to be very particular. So just be aware. All right, so 54 kilograms of one. We need to go to pounds. So kilograms in this case needs to go on bottom. So 1 kilogram is 2.2 pounds. So again, this just ends up being a multiply problem. 118.8. All right. How about, so these all end up multiply. I want to do one a little bit different. So how about, I'm going to submit, this is sort of like 49, but I want to do kilograms, ounces to kilograms instead of the other way. So let's do, I don't know, let's do 67 ounces to kilograms. So I'm just going, this one is not on the page. I'm just making it up so we're not always just multiplying. Okay, so how do we do this? So do we have a direct conversion from ounces to kilograms? No, because our kilograms, it goes to pounds, or ounces go to grams. Okay. Now, and again, this is one where we have two different conversions. My recommendation, one, hopefully in MATLAB, they'll only give you one of these, not both, to kind of avoid the confusion, or they'll have it set up so that MATLAB will accept either answer. But depending on which one you start with, because of the rounding issue, they will be slightly different. So if I was coding this problem, since I'm starting with ounces, I would want you to use the 1 ounce is 28.3 grams. So we're going to start with that one because that is our starting unit. So we know 1 ounce is 28.3 grams. Well, how does that help us? Well, we do know grams to kilograms because 1,000 grams is 1 kilogram. K means the 1,000 of the smaller unit. So now we can set up a problem. And so 1 ounce is 28.3 grams. So the ounces cancel. Now to get rid of the grams, we have to do grams on the bottom. So 1,000 grams is 1 kilogram. So now we're just left with kilograms. And so again, multiply everything on top, multiply everything on bottom, do the division last. 1,000 on the bottom, on the top, 67 times 28.3 gives us 1896.1. Do not round that, or cut it off. When you're in the middle of a problem like this, carry all your decimals. So if that happened to be a longer decimal, carry all those decimals until the very end. Then we divide that by 1,000. So 1.8961 kilograms. I'm going to assume in MATLAB that they don't want more than 2 decimal places. So let's round this to the nearest hundredth. That means we're rounding the 9. The 6 says to round the 9 up. Well, 9 becomes 10, so we're going to round 1 there. That becomes 1 point. So how do I turn that off? 1.90 or 1.9. Either one should be acceptable. MATLAB doesn't like those trailing zeros. So if this was a MATLAB question, they would probably require 1.9 kilograms. Okay, on a test, I've said 1.90. All right, but that's where, again, with two-step process, sometimes you multiply, sometimes you divide. Again, I always recommend doing all the multiply on top, all the multiply on bottom, so you have a single number divide that avoids any order of operations issues. Okay. So that is mass conversions. Yeah, so there's English to English, metric to metric, English to metric. Again, as long as you know your conversions, then it's a straightforward process, just like 9.1 and 9.2. Now, the other things in 9.3 is we're doing temperature conversions. So for temperature conversions, you need to know these two formulas. Now, the formulas are going to be given to you. You don't have to have them memorized. You just have to know how to use them. And notice that there's one for F equals and one for C equals. So how do you know? And so in this case, we don't need the fraction stuff. We're just plugging into formulas. And how do you know which one to use? Well, let's see how we do this. So convert between the two temperature scales. So we have 59 degrees C is equal to Fahrenheit. So which one of these makes more sense to use? Well, if we're trying to find Fahrenheit, use F equals. If we're trying to find C, then use C equals. And so what this tells us, like here on number 58, 59 degrees Celsius, they're telling you what C is. And when you just plug that into the formula and do the arithmetic. Let's figure it out. Okay. So let's convert 59 degrees C Celsius to Fahrenheit. And so since we're trying to find Fahrenheit, we're going to use F equals. Now there is a fraction in these, but again, in the answer, we want either a whole number or a decimal. So that what this tells us is that C is 59. So you just plug that in to get 9/5 times 59 plus 32. Well, how do you deal with this? My recommendation is, since we're dealing with a fraction, put that over 1. So you have, 9 times 59. I just have to do my multiply first. 131 over 5 plus 32. Now this is where do your division. 531 divided by 5 is 106.2. So we want when we're dealing with these temperatures, we don't want the fraction, we want the decimal. So then just add 32 to that, it'll be 138.2 degrees Fahrenheit. That's how you convert Celsius to Fahrenheit. Plug it into the F equals formula. Do your arithmetic and you're good. Okay, so how about the other one? All right, let's and we can have some negative, like let's say it's really cold outside. Hopefully it doesn't get this cold here, but let's say that we get to like negative 10 degrees Fahrenheit. And we want that in Celsius. Well, we're trying to find Celsius. So now we want the C equals formula. So we want C equals 5/9 parentheses C minus 32. I'm sorry. I thought I had that turned off. Right. Yeah, doesn't make doesn't make much sense to have C in the formula both times. So that's supposed to be F inside there. So that's the proper formula. I apologize. So C equals 5/9 parentheses F minus 32. All right, so how do we convert negative 10 degrees Fahrenheit to Celsius? Well, you just take that, plug it in. We get C equals 5/9 parentheses negative 10 minus 32. And now you do the arithmetic. Well, order of operations says we do inside first, inside parentheses, negative 10 minus 32. If you're a little iffy on your negatives, use your calculator. Those are both negative, so we're adding. That's going to be negative 42. Now, what do we do with that? Well, again, I always like to put my whole numbers over 1 to make them fractions in this case. So 5 times 42. That's 210. So we got negative 210 over 9. And then just do the division. So this is negative 23.333 forever. And then this, when in doubt, we're going to assume going to the nearest hundredth. And unless MATLAB says otherwise, so that 3 says keep the 3 the same. We're at negative 23.33 degrees Celsius. Okay. That is all you have to do to convert between Fahrenheit and Celsius, is know which formula to use, and then just be able to plug the number in and do the arithmetic. We did this is one of the reasons why we did those formula problems at the end of unit 1. This is for this unit, and we're doing this for temperature conversions. When we get into geometry, we're gonna have to plug into stuff. So all right, so that is another big part of 9.3 is being able to do temperature conversions using these formulas. Did I make it? Just to double check. Yes, on the formula sheet, I did get the F in there. All right, so the last part of these problems is, or of 9.3 is word problems. All right, there's a variety of different word problems. And so this is where it's really important to kind of, don't just jump into it, start manipulating numbers to kind of figure out what's happening. Yeah. So I talked about drug dosage calculation problems. This is one of the reasons we're doing this for a lot of those for you allied health students. This is a problem I took directly from one of the students I was helping. So let's see if we can walk through this. I actually don't know if MATLAB gets this complicated, but I do want to kind of go through this just because this is like a real world problem, sort of thing. So the recommended dosage of drug ampicillin for pediatric patients, is 200 milligrams per kilogram of the patient's weight. How many milligrams of ampicillin should be given to a patient who weighs 39 pounds? All right. So remember what I said we need to know for these conversion problems? We need to know where we're starting, what we're trying to end with, and then we need to know the conversions. So on all these problems before, without the word problem aspect of it, this was a very straightforward sort of setup. Now that we have word problems, it's not always going to be that clear. So first thing is what are we starting with here? Okay. The recommended dosage of the drug for pediatric patients is 200 milligrams per kilogram. So here's a hint. In word problems like this, anytime you see something with 2 units, and the word per, that is going to be a conversion. So that's not our starting, that's not our ending. I can't say that's 100% of the time, but the vast majority of the time, that's going to tell us one of our conversion fractions. So that's per the patient's weight. So how many milligrams? So here's the key. How many milligrams? That is what we want. We're going to end with milligrams. And then how many milligrams of ampicillin should be given to a patient who weighs 39 pounds? So that 39 pounds, that's what we're starting with. All right. So we're starting with the patient that weighs 39 pounds, and we need to figure out how many milligrams of medicine to give. How do we set this up? Well, again, this is why we did the basic setup on this, even though it had to. So because when we get to problems like this, the process comes in handy. All right, so we have 39 pounds. What do we need to convert that to? Well, for the medicine, it's milligrams per kilogram. We don't have kilograms, we have pounds. So we need to convert pounds to kilograms. How do we convert pounds to kilograms? Well, 2.2 pounds is 1 kilogram. So now we've taken care of the pounds. Now here's another thing is when you think milligrams, often you just think like a small weight, but this is milligrams of medicine, whereas this is like kilograms of person's weight. So sometimes, like in chemistry, you can be dealing with the same like named unit, but we're talking about different things. Like might be talking about mass for like molecules of O2 versus mass of molecules of like H2O. So a lot of times the unit itself is only part of it. It's like, yeah, there's like a bigger picture. So that's 200 milligrams of medicine, not 200 milligrams of weight. So how do you, and it's important because now we need to go from kilograms to milligrams. And so for 1 kilogram, don't put we don't want to go to grams and then to milligrams because we're not converting kilograms of weight to milligrams of weight. We're converting kilograms to milligrams of medicine. So 1 kilogram of patient weight is 200 milligrams of medicine. So now we have the final units that we want. So again, like for our problems, I don't think we have any actual drug dosage calculations in the homework, but for those of you in allied health, you're going to see problems like this. So again, I got this problem directly from helping one of the nursing students. Okay, so now you multiply everything on top. So 39 times 200, 7,800 over 2.2. Now we divide. Now this is 0.4545, so I'm going to round to the nearest hundred, so that'd be 0.45, so 35, 45.45. That's that seems like a lot of medicine, but then like the other thing with like these medicine problems is then you have to worry like, like this is like the total dosage, and then you're given so much per 8 hours, and that definitely goes beyond what we're doing for this course. But for allied health students, this is again, you were one of my target groups on why we're doing all these conversions. This is what we're doing in this class is just a setup for problems that you'll be doing later. All right. So how about maybe like a more like some better like homework question for this class? Let's look at 63. All right, so you're building a fence on your property. You need to buy 8 fence posts at the lumberyard, each measuring 6 foot. Oh, wait. This was from, we're not going to do one of those with measuring, mixing feet and inches. That was the other book. So let's go to the next. These are more from the old book. So rather than do these, let's go straight to MATLAB. Because the old book had the type of word problems were a little bit different. So I need to update my notes a little bit. All right, so yeah, so here is, that one we just did with negative 10 degrees Fahrenheit. Notice that in the problem, they give you the two formulas. You just have to know since you're trying to find C, you're using C equals. We basically did that problem. Oh, there is a drug dosage calculation. Okay, um, so 62 is just like pretty much like 21. Now notice here, they use the fact that 1 pound is 0.45 kilograms. All these other problems, we've been doing 1 pound is 2.2 1 kilogram is 2.2 pounds. And whoever coded this problem wants you to use 1 pound as 0.45 kilograms. So just again, read the problem. But that's that's sort of the same sort of basic problem. Let's do this. Actually, I may come back and do that one after we do it. So here is 22. So the cost to mail a letter is 40 cents for mail weighing up to 1 ounce and 28 cents for each additional ounce or fraction of an ounce. Find the cost for mailing a letter that weighs 88 grams. All right, so what do we know? We know that it's 40 cents for 1 ounce. It is 28 cents for each additional ounce or part of an ounce. And we want to find the cost for a letter that weighs 88 grams. All right, so why is this a dimensional analysis problem? Well, because we're given something in grams, all the cost is dealing with ounces. Okay, so it's kind of hard to know the cost when we don't know the ounces, right? So that's step one, is convert grams to ounces. We have 88 grams. So what is our conversion for grams to ounces? This is a weight. So, sorry, this be helpful. I'm working on my paper. It would be helpful if I actually show you the paper. So that's one of the things with the word problem is first thing I did was write out the information. So 40 cents for the first ounce and 28 cents for each additional ounce or part thereof. And then what is the cost for 88 grams? Okay, so first step one is we need grams to ounces. And so how do we do that? And we're in weight. So 1 ounce is 28.3 grams. So we need the grams on the bottom, 28.3 grams, 1 ounce. So 88 divided by 28.3. Okay, so what do you do here when you have this big old long number? Well, if we were converting to something else like this, then I would just say keep that whole number and then multiply or divide. But here we have a word problem, so a bit different. It's 40 ounces for the first ounce, 40 cents for the first ounce, and then 28 cents for each additional ounce. So when I see this, that is 3 whole ounces and then part of another. So how do we figure out the cost? Well, the first ounce is 40 cents. First ounce equals 40 cents. And so what that means is, how many ounces do we have left? Well, that's 2.10944 ounces left. So how much do those cost? Well, it's 28 cents for each additional ounce or part thereof. So we have 1, 2, and a part. So that is 2 ounces plus a part. So how much do each one of those costs 28 cents. So that would be 3 times 28 cents because the 3 comes from those two are 28 cents, that one each, and then that one is 28 cents as well. But sometimes there isn't all like formula on some of these word problems. Kind of have to use your common sense occasionally. So basically what this means is like for each, once we take the first ounce out of it, for 0 to 1 additional ounces, it's going to cost like 0.1, like 0.01 ounce to 1 ounce is going to be 28 cents. And then from like 2.001 to 3 ounces would be 28 times 2. For in this case, we have a little bit more than 2, so that's basically counting for 3. That's where we're getting the 84 cents. So then the total cost is the 40 cents for the first one, the 84 cents for the additional ones. So that would be $1.24. Okay, so these word problems, you're going to have to kind of think through them. It's not just a straight conversion problem all the time. All right. I don't want to go back and do that dosage problem. So we'll go back to MATLAB. All right, so for 21, we have the prescribed dosage is 8 milligrams per kilogram daily. 8 milligrams per kilogram daily. So that's going to be a probably important number, meaning that 8 milligrams of the drug should be administered daily for each kilogram of the patient's weight. So how many 100 milligram tablets? So we're dealing with 100 milligram tablets. Should be given each day to a patient who weighs 167 pounds. The patient weighs 167 pounds. And again, use the fact that 1 pound is 0.45 kilograms. Okay, so how do we do this? How many tablets should that patient receive? Okay, so here's sort of the important information. How do we put this together? Well, and again, this is something that I've done a lot of dosage problems. I kind of know the first step is almost always, we use pounds, but medicine is in metric system. So pretty much when you're doing these dosage calculation problems, first step is almost always going to be convert your pounds to kilograms. Looking for pounds to kilograms. So this is just a straight, like we're talking about weight here. 176 pounds over 1. And now we're going to say 1 pound. Don't use 2.2 pounds to 1 kilogram, because that's not how the problem was coded. They're using this conversion instead. So 1 pound is 0.45 kilograms. So 167 times 0.45, it's 75.15 kilograms. Now, what do we do with that? Well, notice anytime you have, like I said, we have 2 units here, that is a conversion. And so notice that we have kilograms, and that kilograms is on bottom. So we can convert these kilograms of weight to milligrams of medicine. But since that kilogram is always already on bottom, that to me is a big clue. Now we're going to convert kilograms weight of patient to tabs. We don't want just milligrams, we need to know how many tablets. So we have 75.15 kilograms. We know for the medicine that 1 kilogram of patient means 8 milligrams of medicine. But this is milligrams of medicine. What they want to know is how many tablets, 100 milligram tablets. So the final answer is going to be tablets. That's what we're looking for. So how do I convert from milligrams to tablets? Well, I know every 100 milligrams is 1 tablet. So this is if you're a nursing student, this is sort of like stuff you would talk about. For this class, may not have that background knowledge, but we're going from pounds to kilograms, kilograms to milligrams, and then milligrams to tablets. So you have to recognize that that's a conversion factor. Now, if it helps, this is probably not a good test question. I haven't looked at the test in a while, so I have to verify that before I say it's not on test, but this might be a little messy for the test. But it's still, like I said, almost half a good surveyor going on to our allied health majors. So this is for you. All right, well, we have tablets now. That's what we're looking for. So now we can just do the arithmetic. We'll play everything on top. So 75.15 times 8. So 1.2. And then on the bottom, all we have is 100. Then we divide those. So that's 6.012 tablets. All right, now, what do you think the answer should be? Don't give me 6.102 because can you give somebody 0.012 on a tablet? And in MATLAB itself, it does say round to the nearest whole number. So we're round, that would be 6 tablets. That's why my other answer seemed kind of big because we didn't convert it to tablets, but that wasn't in the setup. So. All right, so this is the word problems in 9.3 can be a bit messy. I feel like there's supposed to be more basic word problems. That'll probably have to be added next semester. So for those of you this semester, those are your type of word problems is one of these dosage calculations, and then the other one was the there's the chemistry one. Let's do the chemistry one too. Yeah, like I said, that's since a lot of you are going on chemistry or science and allied health, we have some of the stuff in here just for you. All right, so the label on a bottle of medicine is each. Is that the one I was looking at? No. Okay. This is more allied health, but also a chemistry sort of question as well. All right, so the label on a bottle of medicine reads each 5 millimeter teaspoon contains glucose of 170, and so 1.87 grams. Let's see how to read this. Yeah. So the number out, okay, yeah. So each 5 milliliter teaspoon contains glucose of 1.87 grams. That seems a little weird because in English we'd probably say 1.87 grams of glucose. But that's how it's reading. So levulose, if I pronounce that right, there's 1.87 grams of that. And then for phosphoric acid, there is 21.5 milligrams. It may seem weirdly worded, but that's how these problems are worded in the context of those courses. Find the amount of phosphoric acid and a recommended dosage of 2 teaspoons. Okay. So what are we doing? All right. So this is where figuring out where you're starting and where you're going is important. So find the amount of phosphoric acid. So that one's nice because we know we're dealing with phosphoric acid and this 25.1 milligrams. We don't care about the levulose or the glucose. So those are extraneous numbers for part A. So all we care about is these 5 milliliter teaspoons and the phosphoric acid. Here's a question. Do we even care about those 5 milliliters? Because it says find the amount of phosphoric acid in 2 teaspoons. We actually don't even care about that 5 milliliters. All we care about is the teaspoon. It just so happens that 5 milliliters is 1 teaspoon. That's sort of what they're saying. But for these conversions, what we're starting with is 2 teaspoons. Let me get back to paper. We're starting with 2 teaspoons. And we want to go to how much phosphoric acid there is. Well, what's the connection is 1 teaspoon contains 21.5 milligrams of phosphoric acid. So 1 teaspoon contains 21.5 milligrams of the acid. So this is something that you're gonna have to do like in a chemistry. This is why I was thinking it was chemistry, is like the milligrams is not of weight, of just like general like body weight or something. It's specifically for the phosphoric acid that we're talking about. So 1 teaspoon has that many milligrams of that acid. And so that's all we're looking for is how much acid we're getting. So this is just gonna be 2 times 21.5. What is that, 43? Of phosphoric acid. So and think of it this way, 1 teaspoon is going to contain 21.5 milligrams of the phosphoric acid. So if we have 2 teaspoons, we just multiply that times 2. Yeah. What about the next one? So if a bottle contains 6 ounces, find the quantity of phosphoric acid in the bottle. So we're going to start with 6 ounces. And then we want, what do we want? We want the amount of phosphoric acid. So again, for this problem, we don't care about the glucose or the levulose. Those numbers are completely like red herrings in this case. And so how do we do that? How do we get from 6 ounces to the phosphoric acid? Well, we know we have 5 milliliter teaspoons. So how do we go from ounces to teaspoons or ounces to the 5 milliliters? Well, the other thing they give us in the problem is that 1 ounce is approximately 30 milliliters. And they also give us that 1 teaspoon is approximately 5 milliliters. So we know if we have teaspoons, we can get the amount of acid. How do we get from ounces to teaspoons? That's what these two conversions are for. Because ounces can take us to milliliters, milliliters can take us to teaspoons. And then once we have teaspoons, then we know there's 21.5 milligrams of acid equals 1 teaspoon. So this is actually a 4-step conversion. So we're starting with 6 ounces. We need 1 ounce is 30 milliliters. Now for milliliters, we need to go to teaspoons. And so on problems like this, it's the key is trying to like follow the trail of the units. Right. We know we're starting with ounces. We want milligrams of acid. How can we connect the two? And that's why I kind of like part A. That's sort of like the warm-up problem, because you can know now you can go from milligrams of acid to teaspoons, and then we just need this to connect the ounces to the teaspoons. If this is a little confusing at the moment, remember these for our class, these are high-end problems. But again, what we're doing is trying to set you up so that when you get into chemistry or allied health stuff, you have the basic sort of stuff, and then you can do more of the involved problems. But it really comes down to just looking at your units. And so now we know that 1 teaspoon is 21.5 milligrams of acid. That's what we were doing before. Yeah. So now this is again the case where multiply everything on top, multiply everything on bottom. On top we have 60 times 30 times 21.5, 38,700. On the bottom, we're just dividing by 5. So 7,740 milligrams of that phosphoric acid. That is how much is in a 6-ounce bottle of this medicine. Okay. So again, this is the power of unit conversions is being able to start something, in this case, like a bottle of medicine, and figuring out like the individual parts of the medicine and being able to convert, in a multitude of steps. And so for those of you going into chemistry and your allied health stuff, this is eventually where you're going to have to go. For us, but in this class, for the most part, it's one step conversions, a few two or a few three, like the miles per hour to like feet per second. That was one of the longer problems. But sometimes in these word problems, the hard part is kind of like knowing where you start and identifying, where you're going, and then from there it's just figuring out the conversions. All right. So again, I definitely would not ask this one on the test. I think that's a little bit above beyond. All right. So that is chapter 9. It's all about unit conversions. Most of our conversions are relatively straightforward. But again, use your fraction setup to let you know what goes on top, what goes on bottom, and you make your life a lot more straightforward with this chapter. All right, that's all I have for today. See you soon for chapter 10.